You pressed send on a message to an AI today. Maybe you asked it a question. Maybe you asked it to write something, and an answer came back in 2 seconds. But here is the thing nobody tells you. Something remarkable happened in those 2 seconds. Your message left your phone. It traveled through cables under the streets. It crossed the ocean floor. It woke up thousands of specialized computer chips in a warehouse the size of a city block. Those chips processed your message at the speed of light, and the answer came back the same way. All of that happened before you looked up from your screen. Today, we are going to break down exactly what physically powers AI. Not the software, not the algorithms, the actual hardware, the chips, the buildings, the cables under the sea. By the end of this video, you will understand what people mean when they say compute. You will understand why AI is expensive. You will understand why it is fast. And you will never think about an AI answer the same way again. Let us start at the beginning. Every computer you have ever used has a CPU. CPU stands for Central Processing Unit. It is the main brain of your computer. Your laptop has one. Your phone has one. Even your smart TV has one. The CPU handles everything your device needs to do. Opening apps, loading websites, playing music, running your email. It is incredibly good at all of these things. But here is the key thing about a CPU. It is a generalist. It can do almost anything, but it works on tasks in sequence. A typical CPU has between 8 and 32 cores. Think of each core as a worker, an expert, highly skilled worker who can do any job. Here is the analogy that will make this stick forever. Imagine a pizza restaurant with 8 expert chefs. Each chef can make any pizza on the menu. Thin crust, deep dish, gluten-free, you name it. They are brilliant at variety. But there are only 8 of them. So at any given moment, they can only make 8 pizzas simultaneously. That is your CPU. Powerful, versatile, brilliant at complex, varied tasks. Perfect for running your operating system, your browser, your apps. But AI needs something completely different. AI does not need versatility. AI needs to do one type of calculation millions of times, all at once. And a CPU was simply not built for that. This is where the GPU comes in. GPU stands for Graphics Processing Unit. It was originally built for video games, specifically to render the pixels on your screen. 60 frames per second, millions of pixels, all updating simultaneously. And the GPU was built to handle exactly that. Massive parallel computation. The same calculation done millions of times at once. Then, researchers discovered something extraordinary. That is exactly what AI needs too. AI models are fundamentally just math. Enormous amounts of multiplication and addition done on huge grids of numbers called matrices. And the GPU was already perfectly designed for this. Back to our pizza restaurant. But this time, instead of 8 expert chefs, you hire 10,000 workers. Each one can only do one thing: put cheese on a pizza. That is it. They cannot take orders, they cannot make dough, they cannot even talk to customers. But when you need 10,000 pizzas with cheese at the exact same moment, they finish in 1 second flat. That is a GPU. Now here is the number that will reframe everything. A modern CPU has 8 to 32 cores. The NVIDIA H100, the GPU that powers most large AI models today, has 16,384 cores. That is not a typo. 16,384 cores. All doing math at the same time. When an AI model like ChatGPT processes your message, it does not use one GPU. It uses hundreds of them, all working together, splitting your request across thousands of chips simultaneously, and finishing in milliseconds. That is why when people in AI news say compute, they mean GPU power. More compute, more GPUs, more parallel processing. And more GPUs means smarter models, faster answers, and higher costs. Which is why AI companies spend billions of dollars on this hardware. So where are all these GPUs? They do not live in your laptop. They live in data centers. A data center is a massive building, sometimes the size of several football fields, sometimes larger, packed floor to ceiling with computers, running 24 hours a day, every day of the year, never stopping. Inside a data center, the GPUs are installed in machines called servers. A server is just a powerful computer with no screen, no keyboard, no mouse. It sits in a tall metal shelf called a rack. Racks are stacked side by side in long rows. The rows stretch down the length of the building, sometimes for hundreds of meters. A single large data center can contain tens of thousands of these servers, and each server can hold multiple GPUs. The companies that build and operate these buildings are called hyperscalers. Google, Microsoft, Amazon, Meta. They build data centers all over the world, specifically in locations with cheap electricity, cold climates for cooling, and reliable internet infrastructure. Imagine a city whose entire population consists of calculators. Every building is a server rack. Every citizen is a GPU. When you send an AI a question, that entire city wakes up. Thousands of GPUs collaborate across dozens of racks. They split your request into pieces. The pieces get reassembled into your answer. And it all gets sent back to your phone. You never see the city. You just get the answer. Now here is the part that stops people cold. We have talked about the chips. We have talked about the buildings. But how does your message actually get from your phone to that data center, which might be on a completely different continent? Most people assume it travels through the air, satellite signals, wireless transmission. But that is not how it works for most data. The answer is underwater cables. Right now, at this very moment, there are over 1.4 million kilometers of fiber optic cables sitting on the ocean floor, stretching across every ocean on Earth, connecting every continent. These cables were laid by ships over decades. They are roughly the diameter of a garden hose. On the outside, they are armored in steel wires. On the inside, they contain strands of glass, strands thinner than a human hair, and data travels through those glass strands as light, actual pulses of laser light, toggling on and off billions of times per second. Each pulse of light represents a piece of your message. And light in fiber moves at roughly 200,000 kilometers per second. Let that sink in for a moment. 200,000 kilometers every second. The distance from New York to London is about 5,500 kilometers. At the speed of light in fiber, your message crosses that distance in about 28 milliseconds, less than the time it takes to blink. The entire round trip, New York to a London data center and back, takes under 60 milliseconds, less than the time it takes to blink. The entire round trip, New York to a London data center and back, takes under 60 milliseconds. You press send. A beam of light leaves a cable junction in New York. It races along the ocean floor. Through the mid-Atlantic, it arrives at a data center in London. The GPUs process your message. The answer becomes another beam of light. It races back across the ocean floor and appears on your screen. Before most people can even register that they pressed a button. This is not science fiction. This is the physical infrastructure that exists right now under every ocean, carrying your AI requests every day. Let us put it all together now. You open ChatGPT on your phone and type a question. Step 1. Your phone's CPU breaks your message into tiny pieces called packets. Each packet is a small chunk of your data. Your phone sends those packets wirelessly to your home router. The router sends them into your internet provider's network. Step 2. Your packets travel through fiber optic cables under your city streets. They reach a major internet exchange point. This is a physical building where different internet networks connect. From there, depending on where the nearest relevant data center is, your packets might travel across a continent. Or they might travel into a submarine cable junction on the coast and go under an ocean. Step 3. Your packets arrive at the data center. They are reassembled back into your original message by a server. Your message is sent to the GPU cluster running the AI model. Step 4. Hundreds or thousands of GPU cores receive your message simultaneously. They split it into mathematical operations. Every word in your message becomes numbers. The GPU cluster processes billions of calculations in parallel, predicting, token by token, the most likely words for the answer. This entire computation takes milliseconds. Step 5. The answer is converted back into data packets. Sent out through the data center's fiber connections, back through the internet infrastructure, back under the ocean if needed, back through the cables under your city, back to your router, wirelessly back to your phone. Your phone's CPU reassembles the packets, your browser renders the text on screen, and the answer appears. The total time for all of this, from your thumb lifting off the send button to the first word appearing, under 500 milliseconds in most cases. That is half a second. For a request that physically crossed an ocean, was processed by thousands of specialized chips, and came back as a complete, coherent, intelligent answer in the time it takes to blink. So the next time you use an AI tool and an answer appears on your screen, you now know what happened. A CPU on your phone managed the request. Fiber optic cables carried it at the speed of light. Possibly under an ocean. A data center somewhere in the world received it. Hundreds of GPUs processed it in parallel, and the answer came back the same way it went. All of that in half a second. This is why AI is expensive. The GPUs cost tens of thousands of dollars each. The data centers cost billions of dollars to build. The undersea cables cost hundreds of millions to lay. This is why AI companies raise so much money. They are not paying for software. They are paying for physical infrastructure at a scale that is genuinely hard to comprehend. And now you understand it. That is exactly what this channel is for. Taking the things that sound complicated and making them make sense. If this clicked for you, follow the AI Stack. We drop a new, plain English AI explanation every single day. No jargon, no hype. Real numbers and real explanations every day. Follow the AI Stack for your daily AI drop. Plain English, real infrastructure every day.